let's have a chat about springs then.
Spring.
So we got two different springs, right? One that's just hanging there with nothing attached to it, and then a second one where a mass has been attached. And what do we notice has happened to the spring when we attach that mass, that exerted force on that spring? It's stretched, right? So the distance that it stretches is what we call x. And thinking about forces that are acting on it, if we hang a mass on it, which way is that mass exerting a force on the spring? Downwards. And so we're going to have going downwards F force due to the mass. The force of, it's going to be a weight, right? A weight force. We're going to have force due to the mass. But the mass isn't moving. What does that mean?
Velocity equals 0.
Velocity is 0, so tell me about other forces.
Elastic force is equal.
There must be another
It's
force
got
that's
potential
equal.
energy.
What's providing the other force? The
The-
spring. Oh. So let me just
saying
adjust
random
my
shit.
x arrow here and make it clear that the x is downwards, but the force of the spring is upwards. And so if we stretch a spring one way, it pulls the other way.
But
And if you compress a spring, it pushes the other way. So one of the key things about how springy things behave is whatever way you pull them, they try and pull the other way. And so an equation for what the force on a spring, the effect that might have on the spring, looks something like F is minus kx. So what are those letters? Who can tell us about those letters? What do they mean? F is the force of the spring, right? The force of the spring.
X is the distance travelled.
Yeah, stretch. And be careful because they always try and tease you into thinking that it's the length of the spring and not the change in the length of the spring. But the x is how much the length of the spring has changed when the force was applied. What about another one?
The spring constant.
So the k is the spring constant, right?
Yeah.
And if it's big, that means hard to stretch.
Big boy.
So if you get some big number, that means the spring is less springy. It's harder to stretch. What about that minus sign? Everyone's been working around the minus sign. We're going to talk about the minus sign. What does that mean?
It moves
downwards.
What moves downwards?
The
Oh, it's
spring
opposite.
pulls.
Opposite. Good. You're going to expand on opposite.
Opposite opposite to the
It's just direction of stretch.
the
What's opposite to the stretch?
The force of the spring.
Good. So the force and the stretch are in opposite directions.
yes. That's what it means. I'm so glad it's recording.
Yeah. Oh wait, it's not even recording. I'm just kidding, guys. You guys actually got pranked. It's not even funny.
really
It's
pranked
literally
us.
not funny anymore. You guys got
Not even
pranked.
fun. I didn't joke about it.
Just doing away for a minute with the minus sign and thinking about what the size of the force does as we change the size of the stretch. We can see that the size of the force goes up and up and up and up and up. So the bigger the stretch, the bigger the force. And that has a weird implication when we come to calculate work done. We can't just do work equals force times distance because every distance has a different force associated with it. And so to work out how much work we've done to stretch a spring, we have to think about the area under the graph. If the force was just constant, if it was just a straight line, then we could just do work equals force times distance. We get the same answer, because it's not, because it's a an increasing force with an increasing distance. That's why we have to think about the area under the graph. And so, how do you calculate area under the graph? What's the shape?
Triangle.
And so, how much, so we know that at any point the height of it is kx. And so we could write that the work is half of the base, which is just x, times by kx. Half of x times kx, what does that change it to?
Half of kx squared.
Work is equal to half kx squared. And so the work done to stretch a spring
Is
and
the
a nice,
same as the potential energy.
yeah, beautiful little circle that we've just created there, right? That we've ended up where we started off.
Faster.
Bang! That the work done to stretch the spring is just the same as the amount of energy that we store inside the spring. We call that
That's crazy cool.